we were talking about motion in space. And so here's my favorite, one of my favorite vector functions, which is this, this one here. So here we've got this vector function. Remember the idea of a vector function. A real value goes in, t, and a vector comes out, right? That's a vector function. For every real value of t, we get a vector. And I'm showing those vectors as t increases here, those black vectors. So here's my current value of t down here. And then for every current value of t, you have a vector. If you let t increase, then, and put all those vectors in standard position, the tips of those vectors sweep out a curve. And the points of that curve are the same as the components of the vectors. That's why a vector function is a representation, that's why a curve in space is a representation of a vector function. Because it's basically all those vectors as locations, as ordered pairs in space, ordered triples in space. Okay, and so then we said if the most common application of this was like position, like this vector is a position function. And so then what would the velocity function be? So if this is position, not again.
Velocity would be the derivative of the position function.
That's right. That's right. So RT is a position. Then the velocity function would be R prime of t. And what did we say about that? We said that we want to show that not the way we're showing this vector function. So this is a new vector function. We want to show that one with all the tails of its vectors at the point in question. And so I'm showing that now. So here's the velocity function I'm showing in blue. It's also a vector function, but better suited to be shown like this because it shows the direction of motion and also the magnitude of the speed, right? The speed at which the path is being swept out. And so if this is an object, that's the speed of the object. Okay, so then a direction of motion function, if we don't care about the speed anymore, we just want direction, how did we get that?
Unit vector.
Yeah, so we make that one. So we're gonna take the velocity function and unitize it. So this is called the unit tangent vector. It has the exact same direction as the velocity function, but it's a unit vector, right? So it's pointing in the direction of the curve or the direction of motion, but it's a unit vector. So so we don't care about the speed anymore. All right, what is our speed function? What is our speed function? Well, that's the magnitude of this, right? So the direction of motion function is the direction of the derivative. The speed function is the magnitude of the derivative. So that's this. Now that's no longer a vector function, right? You take the magnitude of it, you get a real valued function. So you put a t in, you get a number out. Just how fast, just the speed. Okay. All the other ones so far have been vector functions. You put a t in, you get a vector out. Okay. So we're going to advance the conversation here. And so I want to draw a picture. Pause this. And actually, let's turn it off. And so here we've got our, so say I've got some function like this through space, okay? It's going through space like this. And here we are, right here. So for some value of t, there's an r of t like this. Okay, so that's r of t. So I'll call it t naught. And so using like a clock, what number on the clock would it point to the t, the unit tangent vector of t naught? So it would be pointing towards 11 o'clock or 5 o'clock or 3 o'clock. Which direction would t be pointing right now? So assuming that the direction of the curve is this way. So increasing t, as t increases, the curve sweeps out this way.
3 o'clock?
So 3. Yeah, 3, maybe 4. So it's kind of bending down there a little bit. So that would be, if I'm just care about the direction, that would be my unit tangent vector at t naught. Okay? What vector has the same direction as that?
Velocity.
R prime of t naught, right? So R prime of t naught would have the same direction, but it would also include the speed as its magnitude. This is just a unit vector pointing in the direction of the curve. Okay, and so we want to look at something else here. Let's see. If we let time increase a little bit, so let's say to take us to this point, then would the new unit tangent vector, would it be pointed more horizontal or pointed more down?
More down.
More down, right? So here's, say, the original one, and I'm going to, for dt, the next unit tangent vector would be like this, right? So this is, say, t of t naught, and then this one would be t of, what, t naught plus a little more time gone by. Does that make sense? Okay?
Yeah.
And so then what would the vector t of t naught, so we're going to do vector subtraction. I've got it all ready for that because they're tail to tail. What vector would this be? What vector would that be right there if I took this one minus this one? Would it point down to the left or up to the right? If it's this one minus this one. Do you remember?
Point up.
Down to the left.
Down to the left, right? Final minus initial, right? Final minus initial. So this difference would be that vector right there. Okay? And so if I took that difference and divided by how much time went by, right? So the change in my vector per change in time, what is that really representing for a small change in time? Yeah, this is like the derivative of the unit tangent vector. And so which direction does that face? The derivative of the unit tangent vector points this way. Right, like that. I'm going to make a little water. You see that? So that's the same direction as this. Okay? And so now I want to unitize that. So I took this is taking the derivative, looking at a little change in time, looking at the new unit tangent vector. And so this is the difference between those vectors. If I take that difference between those vectors per unit time, I'm really just taking the derivative of the unit tangent function. And now I want to unitize that. So I take the derivative of the unit tangent function and unitize it. And so now I've got this vector right here has length 1. Okay? How is it related to, so how is that related to our unit tangent vector. Do you see how it's related directionally?
Orthogonal.
Yeah, it's going to be orthogonal. Imagine a really small dt. It's going to be orthogonal to it. Okay? And so what this is called, because it's orthogonal to the tangent vector, it's called the unit normal vector. Sorry, this is a function. There shouldn't be t notes here. So this is just taking the derivative of the unit tangent function and unitizing it. That gives us a function called the unit normal function. So if the unit tangent function gives us the direction of motion, or the direction of the velocity, then what would the unit normal direction be? Does anyone see what that would be? Here we're coming along the curve like this. What does the unit normal, what direction is that for our object? What does it mean for our object?
Is that the acceleration?
No, not quite. It's related. We'll see that later. But
Let me
what?
take a guess and say the direction of turning.
Exactly. So which way are we turning? We're in a car here. So here we're in a car. Are we turning, if we go this way, are we turning right or left? Are we in a right-hand turn or a left-hand turn? Going this way. Right, right? We're turning right, right? Our car is turning to the right. That vector is telling us that. It's perpendicular to the plane of the direction of motion, and it's saying you're turning right now. So it's the direction of turning, someone said. Perfect. Can you still see me writing down there in the corner? That's still showing up down there? Good. So we've got the unit tangent function. That's a unit vector that gives us the direction of motion, or the direction of the velocity. Now we have another similar vector. It's called the unit normal function. The unit normal vector function is giving us the direction of turning. So if you're in your car, that n will always be either straight out the passenger side window or straight out the driver's side window, orthogonal to forward. Right? Forward is the direction of t, and then either straight out your passenger side window if you're turning right, or straight out your driver's side window if you're turning left. It's either one of those two always, because it's orthogonal to the direction of motion. Okay, does that make sense? Okay, so now I'm going to come along. So we got unit tangent. So the direction of turning function, that's this, n of t. And what is that? We get that by taking the derivative of the unit tangent function and unitizing it, make it a unit vector. So now there's one more function, and that's what you get when you do t cross n. T cross n. What happens when you do a cross product? You get a vector that is orthogonal to both the original two. That gives two possible directions, right? That gives two possible directions. So what would the two possible directions be here for this cross product? Either coming out at us or back into the screen. So by the right-hand rule, which is it? Coming out at us or back into the screen? If you put your index finger this way of your right hand, so that your third finger points kind of down.
Into the page.
Yeah, then your thumb will point into the screen. This is called the binormal unit vector. B for binormal. So this would be b of t naught. And it's orthogonal to both of those other two. So what you have with these three vectors, these three unit vectors, is you have like a little R3 coordinate system that moves in space with the object, such that t is always pointing straight out the front of the car, direction of motion, and is always pointing either straight to the right or straight to the left, depending on according to which way you're turning. And then b What B would be pointing like straight up the roof, out the roof of your car, or straight down into the ground. Okay? So in this case, it'd be, so we're moving this way. So in this case now, so like the top of the car is facing us, right? So if we're turning this way and we're going this way, then the top of the car is facing us. So B is pointing straight down into the ground, perpendicular to the, like a vertical line straight into the ground. If this is our car driving on the road like this. Okay, questions on this. So these are a set of 3 unit vectors that form a 3D coordinate system. Just like I, J, and K, those were I, J, and K formed our R3 system. So now T, N, and B form a moving R3 system that goes with the object along the path. Questions? Does that make sense?
Yeah, so what would B actually represent in terms of motion of the point or the car?
Actually, the direction does not have a meaning for the motion of the car. So T and N are what form the motion of the car.
Okay, got it.
Yeah.
So is B, is that a unit vector as well?
Yes.
Just
If you
going
take
down?
a unit,
Okay.
right? If you cross product 2 unit vectors, you'll get a 3rd unit vector. So yeah, these are all unit vectors.
All right.
So what the acceleration function be the second derivative of R?
Oh, you're ahead of me. You're ahead of me, John. That's what we're going to do next. So that's the right question, because that's what we're just about to do that. But we have to talk about one more thing first. Can you wait a little bit? All right, so with this coordinate system comes 3 planes, 3 coordinate planes. Okay? So there is the plane of, let's do the normal plane. So the normal plane is kind of the easiest one to conceive. The normal plane is the plane that the curve pierces through at a right angle. Okay, so that's the normal plane. The normal plane pierces through at a right angle. Which 2 vectors form the normal plane? If it's the plane that this pierces through at perpendicular to the plane.
Is that N and B?
He wants N and B. The rest of you agree? Yeah, that's right. So the plane of N and B will be the plane that the curve is normal to. Now, if I want to write the equation of that plane, I need an orthogonal vector. Which vector is orthogonal to the normal plane?
The acceleration, I'm assuming. T.
T. Notice, it's the normal plane, but to write its equation, you don't use the normal vector. You use what? T. You use T to write its equation. Because T is orthogonal to that plane, which the curve is orthogonal to, right? All right, the next one is a tangent plane. The tangent plane. The tangent plane is where the curve comes and just touches for a point, like a tangent line touches a tangent circle. So which plane does this curve come up and just touch at a point and then leave?
T and B.
BT.
T and B. So notice it's the tangent plane to the curve, T and B. So it's this plane here. Which of those vectors do you use to write its equation?
N.
N. So notice it's the tangent plane, but to write its equation, you use N because N is orthogonal to the tangent plane. Does it make sense?
Yes.
Okay, then there's one more plane, and it's called the osculating plane. Not oscillating, osculating. That's the plane of N and T. So what is that? And then we're going to use B to write it. But what is that plane? So that plane of T and N in this example, it kind of looks kind of like it's parallel to YZ a little bit. It's kind of like a vertical plane, something like that. Okay? So what does that represent for the car's motion? The plane of T and N. So it's actually the plane of motion. It's the plane that the curve is in at that moment. If you think about taking 2 points really close together there at T naught, like just 1 point and then the next little microsecond later, take the next point, the osculating plane is the plane that both of those points are in. So it's like the plane of motion. It's the plane of motion. It's the plane that the object is traveling in at that moment. So if you take 1 point and then the next little bit of time you take the next point, it's the plane that both of those points are in. It's the plane of T and N. Does that make sense?
Yeah.
Okay. So any questions? So we got so what we have is we have an R3 coordinate system that's moving along with the curve. You've got the first vector is T, that's the direction of motion. We talked about that yesterday, or on Wednesday. Now we have this new vector that tells us the direction of turning, whether right or left. And then we have a third vector that's the cross product of those two. And that's called the binormal vector.
So, and this works because they're all unit vectors, right?
That's
so it
right.
represents like the point.
It's all unit vectors. So yeah, these are all unit vectors. So let's practice. Okay, so I got an animation with a different curve, and we can practice figuring out what these are and what the three planes are. So before I erase, any questions?
I was just going to ask if T is a second derivative of R.
Something like that, right? We took yes, because T is something of the derivative. T is the unitized version of R, and now we're taking the derivative of it again. So yeah, it's related to something like the second derivative of R. But it is not R double prime. It's not, we're going to do that later. It's not, N is not this.
Oh, okay.
It's not that. But it's related, yeah. It's like it's kind of, T is the kind of the first derivative, something of the first derivative of R. N is something of the derivative of T. But N is not equivalent to R double prime. Other questions? All right, so let's practice. All right, so here I've got this function, and it's a similar one we had last time. And we said it was a helix. It was elliptical in the YZ, kind of parallel to the YZ plane. It was elliptical. And then x just increased constantly. And remember we said, so for that ellipse, so for this particular way I'm defining it, I'm choosing 2 sine t for y and negative cosine t for x, or for z. The y width is twice as much as the z height, so that's the 2 versus 1. And then to do a similar type helix, we could, so here, so with a helix, all right, not a surface, but with a helix, it will matter. You'll get a different helix depending on plus or minus sine, plus or minus cosine, but they'll all lie on the same elliptical cylinder coming out here, coming out the x-axis. So I want you to look at this. I've got a red vector, red, black. So in alphabetical order here, let's see, we've got black, blue, pink, and red. Which is which, okay? So looking at this, what's the blue vector? What's the black vector? What's the blue vector? What's the pink vector? And what's the red vector, according to this conversation we just had?
Is red vector RT?
He wants the red vector as the position function, RT. What do the rest of you think?
I agree.
Yep.
Yeah.
That's an
Coming
easy
from the
one.
org, yeah.
Good one to start on. Yep, that's the good one to identify first. So this is position. Okay, so what's the next one that's logical to talk about?
It looks like blue.
The blue one.
Blue one. Which one? What's the blue vector?
The R prime.
R prime, but
The
as a unit
velocity
vector
one.
is called what? So you're right. It's R.
Is it the T vector?
Yep. So R prime is close. You got the same direction, but these are all the unit vectors. So the blue one is T, which is the direction of R prime. Yep.
And that's the one parallel to the line.
It's parallel or tangent to the curve. It's
Tangent.
pointing. If little t is time, then it's the direction of motion. It's like looking straight out your car. You're driving on a curvy, hilly, banked road, and t is always the direction straight out the windshield, straight forward. Okay, how about we'll just do black next since it's the first in the list. So the black vector.
Since the black one is orthogonal to the blue one, I'm guessing, well, technically they're both orthogonal, but I'm guessing the black one is n.
Turning vector.
Yep, the black one is showing that we're turning. So what way are we turning here? So it's going to start over here soon. Starting over. So if we're in our car.
Left.
Left turn.
Left. Yeah.
Yeah, it's always a left
Yep,
turn.
right,
Please
exactly.
fix.
It's always turning left. And so it's always pointing kind of the center, kind of toward the center of the helix, right? If this was a circular, it would always be pointing right at the center of the circle. But this is elliptical, so it's not quite like that. But that's the general idea. That's pointing towards the center of rotation, right? So black is our n vector. Okay, which leaves the pink one, which is orthogonal to both these two, orthogonal to the plane of motion at that moment. That's the binormal vector. Okay, so let's back it up here. Any questions about that? Does that make sense? So you see you've got this like little R3 coordinate system that moves along with the object as it flies through space. So I'm going to go right out to this point right here. And I'll show you some planes. We're going to tell me which plane it is, right? So here we are. This is actually at pi over 2. T is pi over 2. And let's take a look at this first plane here. So that plane right there, is that the tangent plane, the normal plane, or the osculating plane?
Would it be the normal?
Someone wants the normal plane. The rest of you agree?
Yes.
Yes, right? That's the plane that the curve is orthogonal to at that moment, right? The curve is coming through. It pierces through that plane perpendicular to it. So this is the normal plane. Which vector would we use to write its equation?
And we use the T.
We would the T vector, since that's the one orthogonal to the plane.
Right. Many of you are saying it. So the normal plane, normal meaning normal to the curve. To write its equation, we need an orthogonal vector to that. So that's the tangent vector, that blue vector right there. Okay, next plane. This one. So we have two left. We have the tangent plane and the osculating plane. The osculating plane is the plane of motion, and the tangent plane is where the curve just comes and touches it tangent and heads away. So osculating.
So that's tangent.
This is
This looks like the tangent.
this is the tangent plane. Which vector you use to write its equation?
N.
The n vector.
The black vector, the
Right.
n, right? The n vector, the black one. Okay. Finally, That leaves which one?
The oscillating plane.
So careful.
Skew.
Yeah, it's not oscillating, it's osculating. That's a different word. So oscillating means going back and forth. Osculating means what we're talking about, the osculating plane. And so do you see that that's the plane that the object is traveling in at that moment? Do you see that? Like if you took a point right before and a point right after, it's like all three of those points would be in this plane. It's the plane of motion. Which vector do we use to write the equation of the osculating plane?
The B.
B, right, binormal vector.
Can we see this plane in motion?
Sure. It's not gonna, it kind of cuts out in different places, but you can see it. Yeah, so it was, yeah, so it's gone. So let me go backwards instead of forwards. All right, so there it is. And so what about when we start? When we first start, down there at the bottom, or in the back there, I guess. So it's the plane of motion. And that's the best I can do right there. That's pretty cool.
Okay, yeah, I see. That's cool.
Okay, so questions on T, N, and B vectors and those three associated planes.
Could you go back to the normal plane, please?
Sure thing. That's the first one, right?
Yes.
So here's the normal plane. Always, it's the plane such that the curve cuts through it or orthogonal.
Okay, thank you.
Does that help? And notice
Yes.
its orthogonal vector is always the tangent vector.
So this plane wouldn't include a point where you're currently at, or would
They
it?
all do. They all go through the point on the current point on the curve. Yes, they all go through the current point on the curve. So that's right here, right now. See that?
Okay.
That's like, so the point in question on the curve, the position vector, is like the origin of this system, always. And so all three vectors originate from that origin, and all three planes go through that origin, or contain that origin. So, sorry. So this is the normal plane. Not the greatest view. Oops. Okay, other questions? All right, so I want to show you something new now. Let's keep advancing the conversation here. Erase. Go back to my favorite. And I want to show you still a new vector we have not seen before. So this gold one. So when you watch this gold vector, I want you to watch the direction that it points and its magnitude, but mostly the direction that it points. So here it's pointing kind of back the other way from our derivative, or velocity function. Now it's pointing straight opposite direction of velocity. Now it's orthogonal to velocity as we go around the loop. Now it's pointing the same direction as the velocity. Now over here it's pointing orthogonal again. Here it's kind of pointing forward, but not parallel to the velocity. This is the velocity, this top one here. This is this new vector. So it's kind of has a component in the forward direction, but it's not the same direction. And now it's the same direction again. What's going on here? This is a crazy vector, right? It's doing everything. It's pointing backwards. It's pointing orthogonal. It's pointing, partially forward. Here it's partially forward, but not really the same direction.
Is this the normal vector?
No, so definitely not the normal vector, because it's like right now it's pointing in the direction of t. And earlier it's pointing in the direction opposite of t. It's the direction opposite of t.
This is the acceleration vector.
This
right?
is the acceleration vector. It's pointing all over the place. It's crazy, right? It's like going all over the place. What is going on here? This is indeed acceleration, or r double prime of t. Okay, so does anyone know the reason why it's like kind of going haywire here? It's doesn't really have any direction. It's like it can point in any direction. Does anybody know why?
Because the curve's changing directions and speed all over the place.
Okay. All right, so he mentioned he split that up into two things. He said the curve is changing speed and it's changing direction. Both of those separately contribute to acceleration. So if the curve is changing speed, what direction is that referring to? If the curve is changing speed, that's referring to what direction?
The velocity.
Okay, but
Like
now given what we're learning here,
the velocity.
changing speed, but given what we're learning here about vectors, which vector would be the direction of changing speed?
The derivative of the velocity.
The t, right? That would be the t one.
See.
He also said the curve is also changing direction. What would be the associated vector with that?
Wouldn't that be B? Or no, N?
N.
Then
Remember what we said. What's the plane of motion? The plane of motion is the plane of
Motion.
t and n, right? The plane of t and n, the osculating plane, is the plane of motion at t and n. So for acceleration, you have two components of acceleration. You have an acceleration in the forward direction, t, and you have a component in the direction of turning, n. Right? But you do not have a direction, you don't have a component in the direction of b, because none of the motion is in the direction of b. All the motion is in the t-n plane.
I'm confused. How can I thought speed was a scalar?
I'm saying the associated direction with speed. You're right. You're absolutely right. It's a scalar. But I'm saying that this direction is associated with speed.
Okay.
Speed is how fast you're going, and this associated direction would be the velocity, or t. And so then the associated direction to changing direction, this is easier to grasp, would be n. Which way are you changing direction? That's n. So does that make sense?
Yeah, thank you.
You're welcome. Okay, so So I just want to take you through a slide fast that has some formulas. We're kind of missing some building blocks to these formulas, but it's a 3-hour course instead of a 4-hour course. That's one of the things that I sacrifice here for time's sake. But I just do want to kind of show you generally. All right, where's that? That is, sorry, not surface area. No. Where am I? There it is. Okay, acceleration. So I'm gonna go fast. Don't try to take notes on this. You can pause the video later. But I do want to kind of get back to the visual on it. Just want to get you the formulas. So we said that acceleration just listen and just be engaged here. We said acceleration is the second derivative. But that second derivative is broken up into two components. There's the speeding up, slowing down. And what's the direction of that? Speeding up, slow down is in the direction of t. Turning, which is in the direction of n. Okay? So when we look at it makes sense to talk about acceleration by breaking it up, decomposing it into these two types of acceleration. Then that picture that I showed you is going to make sense. Okay? But if you're just seeing the vector just as itself, just pointing all different directions, it's hard to make heads or tails of that. So this is what our double prime is. It's the scalar tangential acceleration times a unit vector in the direction of t, plus the scalar turning acceleration, or normal acceleration, times the unit vector n. So the second derivative is a vector function, and this is the way to make sense of it. Break it up into its normal and tangential components and look at the normal or tangential acceleration and the normal acceleration. So I'm not gonna do this at all. So we're just gonna, this is how we come up with it. But I want to get back to the pictures. So here's formulas. So for the tangential acceleration, this is scalar now, not vector. It's the derivative of the speed function. So by this is the speed, this is the magnitude of so it's like, this is really what this is saying is our speed function is this one, and that's what I'm calling v of t, not a vector function, just speed. So it's a scalar real valued function. And you take the derivative of that, right? Second derivative, but just of the speed. So that's the tangential acceleration as a number, as a value. So yeah, so you're going to take the derivative of that. Okay? And then the normal acceleration is the speed squared times, well, this is the curvature function. This is something we skipped over. Okay, we didn't do this. But it's based on how fast you're going and how tightly you're turning. That's the normal acceleration. In order to, in terms of calculating them, here are the formulas. So it's going to be r prime of t dot r double prime of t over r prime of t, the magnitude. That's the tangential acceleration. This is a scalar function. It gives a number, not a vector. So this is real valued function. And then the normal acceleration is the cross product of r prime and r double prime over the magnitude of r prime, also a real valued function.
What is the k of t?
This is curvature, which we did not do. We skipped over it.
Okay.
Curvature is like at any value of t, it's like how tightly the curve is. So that's a high curvature. This is low curvature. So when you have high curvature and high speed, your normal acceleration is high. When you have low curvature and low speed, your turning acceleration is low. But so these are the formulas that you can crank out the real valued functions, just the number, the tangential, the speeding up, slowing down acceleration, and the turning acceleration. And then to build it back into a vector function, r double prime, you multiply each of those by the respective unit vectors. So these are the scalar, or just the values of the two types of acceleration, and then multiplied by t and n and add them together, components, you get r double prime, the vector function, which I was showing you in the picture. So quickly, let me show you the picture again. Oh, here we go. This is what I want to show you. So here's some snapshots along the way. So like this one, we're just about to start into the loop here. Which is the direction of the acceleration? It's pretty much solely in the direction of what? Here's the direction of, yeah. So this is the velocity, or the direction of t. Notice the acceleration is pointing pretty much solely in the direction of n. What does it mean? It means at this point in time, there's very little speeding up and slowing down, but there is acceleration due to the fact that we're turning, and that acceleration is towards the center of rotation. So this is like a high n normal acceleration contribution and a very low tangential acceleration contribution. So not speeding up or slowing down very much. but turning, so we have acceleration. Same thing with this one. All turning and no forward change in speed. Therefore, the acceleration vector is like in the direction of n. Okay, what about this one over here? So here is most of the acceleration due to speeding up or slowing down or turning?
Looks like speeding up.
Right. This is mostly pointing in the direction of motion, a little bit to the side. So you have a little bit of turning acceleration, but mostly speeding up acceleration. What about this one right here? So direction of motion down to the left, direction of A is like parallel in the opposite direction.
That's slowing down, right?
Slowing down. What about turning?
Not really turning.
Not really turning, right? So it's like we're going straight, mostly straight, and we're slowing down. So then the acceleration vector is, the biggest contribution is the tangential acceleration, and it's in the opposite direction, meaning we're slowing down. But there, we don't see a component perpendicular, so it's kind of going straight. So we're kind of going straight and slowing down. Okay, what about here? This one, last one. Mostly doing what?
Looks like turning.
Mostly turning, but not turning very much because it's a small vector, right? So the normal acceleration looks small. So we're just turning a little bit. And what about speeding up or slowing down? Not really, right? So it seems like most of the acceleration is in the direction of n. So a little bit of turning and like zero slowing down or speeding up. Here's a lot of turning, right? So the acceleration vector is much longer. So there's a high degree of acceleration due to turning.